me because I have done that before. All right, let's see. Let me make sure I'm sharing via the other recording as well. Start recording. There it is. All right. All right, everybody see the white screen? All right, good. Thank you. All right. So, what do we have so far? What we have so far is the one equation to rule them all. P1 V1 over T1 is P2 V2 over T2, and this is the combined. And when do we use the combined? We have pairs. That's when we use that. And then we had, seems so long ago, PV equals nRT. And this is the ideal gas law. And this is when you have no pairs. And how do we pick our R? We pick R on the units. So, there's two R's that we generally use, and that's 0.821, and that's liters, atmospheres, moles, Kelvin, and the other one was 62.4 liters, millimeters mercury, moles Kelvin. And I let you on to the big secret that was never ever told to me properly, which is how do you pick your R? You base it on units, and typically you base it on the pressure units, but you do have to make sure that all the other units match up. So you may be given a problem that's in milliliters. Well, you'll have to put it in liters, which is why you need to know there's 1,000 milliliters to a liter. And I can guarantee you, and you probably noticed this as you've worked through problems, hopefully you are, that every problem that you're going to get is going to be in degrees Celsius, and you have to add 273.15 to that to get Kelvin. Okay? Guaranteed. Every time. Now, let me make sure I'm going to leave this locked, unlocked. Okay, so guaranteed, I can guarantee you every time you see a problem, it's going to be in degrees Celsius because that's what your thermometers read in. Now, I made the statement a couple of years ago. I said, and you can't get a thermometer that reads in Kelvin. It turns out that if you go to Lowe's, you can find thermometers that read in Kelvin, believe it or not. You can at Lowe's. Okay. So, but in reality, most of the time when you're measuring something, you're going to measure it in degrees Celsius. But these equations don't work unless you use Kelvin. They just don't work. You end up with strange things like negative pressures and negative volumes. So, this is the big don't be that person, right? And I say that, I say, don't be that person. Okay. All right. So the next one that we're going to look at is something called partial pressures. All right. And that is the pressure total is the sum of the individual pressures of the gases. That's what that is. Okay. And this is called Dalton's law. All right. Now, how do we use this? It's addition. This is how we use this. It's addition. Basically, the idea is that if you have a container and it has a bunch of nitrogen in it and you have a bunch of oxygen in it, then the pressure, the total pressure, is going to be how much each of them have, which kind of makes sense if you think about it. It's almost as if the gas particles can't see each other, and they don't. I mean, that's part of kinetic molecular theory, is they don't see each other, and that's the way it works. So you have the pressure total is the pressure of each one of whatever's in there. All right. So here's the big thing. When you're doing this sort of stuff, The one thing that's going to mess you up, you have to make sure that the units are the same. That's the big thing. You have to make sure the units are the same, because it is not uncommon to have something that says something like this. You got a gas mixture and it's 1.100 atmospheres N2 and, let's say 1241 millimeters mercury in atmospheres. Okay, do y'all see what's going on here though? We have atmospheres, we have millimeters mercury. One or the other, you have to change. One or the other. So you can't just add atmospheres to millimeters mercury. You just can't add them, all right, because they're not the same units. And actually, I think I've probably mentioned that before, and some other sorts of problems, that you have to be very consistent with the unit. So what do we need to do here? Well, you know what? I'm looking for atmospheres. So what I'm going to do is I'm going to take the 1241 millimeters mercury, and I'm going to turn that into atmospheres, because that's the only way I'm going to get these things to add up. So what's the magic number? Magic number is 760. 760 millimeters mercury for every atmosphere. And that we can put in our calculator. So let's see, you got 1241 divided by 760, and I get 1.633 atmospheres. About an atmosphere and a half, thereabouts, right? And so what do we do now? Well, we have the pressure nitrogen plus the pressure oxygen gives us pressure total. So this is that many atmospheres of, I guess that's O2, and plus our 1.100 atmospheres of nitrogen, and we just add them up. So we add 1.1 to that, and that would be what? 2.733 atmospheres total. There it is. So where's the part that's going to really trip us up is right here. This is what gets people. All right. They have to be the same units. Whatever it is you're doing, they have to be the same units. That's the big thing about, and this Dalton's law is super easy. But that's, if you're going to get tripped up, that's what's going to trip you up. All right, now, related to this, as far as Dalton's law goes, I mean, Dalton's law is what? P total, P1 plus P2 plus whatever the pressures are. Related to this is the idea of moles. And that is the number of moles, little n, is the sum of all the individual moles. And if you look at this, what do you see there? Well, the amount is the number of moles, right? That's how many atoms you have. Well, it's directly proportional to the pressure as well. Okay. So what you can see is something along these lines. How many atmospheres? And let's see, let me make that mixture look a little better. Mixture of, let's say, 8.00 mole methane, CH4. That should be a 4 there. It should look a little better. Let me fix that 4. There it is, CH4. And, let's say 16.0 mole O2. All right. So we want to know the pressure. We want to know the pressure here, but we have the moles. And so the beauty of all of this is we don't have to do more than one calculation. Really, I have to do one calculation in all of this, and that is that the pressure PV equals nRT. I have the moles. I have moles. And so what am I going to do here? I'm going to say, and we need a temperature too. And let's say we have in a 4.00 liter container at 25.0 degrees Celsius. Okay, so I want to know the pressure, I got the volume, I got the temperature. Okay, so there it is. Okay, so what are we looking for? We're looking for the pressure. And so we say P nRT over volume. How many moles do we have? Now here's the thing. You only need the total number of moles. You don't need anything else. And so what is the total number of moles? Well, it's 8.00 plus 16. Let's make that 00 just so the numbers will work out. And that's what? 24.00 mole. And there you go. So it's 24.00 mole. What do we need to use for our R? Well, our R needs to be in atmospheres. And so we say 0.0821 liters atmospheres, moles Kelvin. And we need to multiply times our temperature. Oh, wait, do we have to be very careful with that temperature, don't we? We don't want to use degrees Celsius. If we use degrees Celsius, it will be one of the answers. It will be one of the answers. It'll be wrong, but it'll be one of the answers. And so that's what, 298.2? And so times 298.2, and then divide the whole thing by the volume, which was what, 4.00 liters? And there it is. We can put it in there. So we say 24 times 0.0821 times 298.2 divided by 4. And I get a pretty high pressure, 146.89, which is what? We have to go ahead and put that in significant figures. And we look through here and we see what? We see 4, 3, 3. There's 4 over there. So I think we should go with 3 sig figs, don't you think? 147 ATMs. Very high pressure, 147 ATMs. So that basically is how that works out. So what's another way that you can see something like this as far as a Dalton's law problem goes? We can start with grams. So we can say, what is the total pressure? We'll go in atmospheres of 4.12 grams of, I don't know, let's go with argon, and 2.18 grams of H2. So what's the total pressure here? And you look at that and you say, you know what, I want the pressure, and I do know that pressure total is P1 plus P2 plus whatever other stuff I have in there. And you may say to yourself, well, I don't have the pressure. But you know what's also true? Moles total is all the moles together. This is also true. And so anytime I see grams, what do I know that's true? When I see grams, I know I'm gonna need the molar mass of each one. And I don't remember off the top of my head what argon is. And so I'm going to look at my periodic table. And what do we see for argon? Argon is 39.9. 39.9 grams argon for every mole argon. And hydrogen, I do know, is 2.02 grams for every mole H2. Yep. All right, so I have these, and so I can easily get the number of moles from each of these. And so let's go ahead and do that. So I say 4.12 grams argon. Draw a line, draw another line. One thing that we should be really good at by this point is being able to cancel units. We should at least be good at that by this point, you would think, because that's really all the whole semester has been about. And so we say a mole argon is 39.9 grams argon. Put that in our calculator. Let's see, 4.12 divided by 39.9, and I get 0.103, and I'm going to go out one extra just for rounding purposes. So I'm not going to do sig figs till the very end. So at the very end, I want 3 sig figs. There's 2 schools of thoughts on sig figs, and one is you round every time you do something, and there's other school of thought, which is what I'm part of. You don't round till the end. If you round early, then you get what are called rounding errors, and I can prove it to you. I'm not going to do that today, but trust me, I can prove to you. Bad idea. All right. So I'm going to carry an extra digit. And so I look over here and I say 2.18 grams H2 and a mole of hydrogen is 2.02. It's going to be a little bit over a mole. And let's see, 2.18 divided by 2.02, and I get 1.079. And let's go and go out one more. Now what do? Just add them up. And so we do that. Let's say 0.1033 plus 1.0792, and I get there you go. Okay, now what? Well, now all I got to do is just plug it in there. So we're still looking for the pressure, and so we can do that, and we say PV equals nRT. I'm looking for the total pressure, nRT over volume. What do we got here? Let me back up just a little bit, and let's see. Hold on. Oh, that's what happens when you have, what is the total pressure? All right, so we need some sort of volume. Let's stick with our container, which we have in our lab, which is 4 liters. Typical room temperature, 25 degrees Celsius, which is, of course, 298.2 Kelvin. And we plug in these numbers, and what do we get? We get 1.1825 mole, 0.0821 liters Kelvin, 298.2. There we go. And over our container that we have, and here we go. So I'm going to take the number that I have still in my calculator times 0.0821 times 298.2, and then we're going to divide by our 4-liter container, and I get 7.24 atmospheres. And there it is. So what's the whole point of all of this? The whole point of all of this is that these two equations, they go together. Okay. So you're going to use them as your first step towards getting to using your ideal gas law. All right. So it's a two-step problem. It really is, in the sense of, you've got the grams. You know that as soon as you see grams, you're going to need the molar mass. And as soon as you see molar mass, you're going to need moles. And then from there, we're going to add up the moles, and then we're going to plug and chug. We're going to plug and chug. All right. So that's how you end up using your Dalton's partial pressures. Okay. Now, the other way that Dalton's partial pressure is used is, let's say you're collecting a gas. Let's say you're producing, say, NO2 in some reaction, and you have it hooked up to a hose. And one way to collect gas is to allow it to bubble out. And so you fill up an inverted container like that. And part of what happens there is, as it goes through, and this is water down here, by the way, as it goes through the water and goes into the inverted cup. I don't know if I remember when I was a kid, um, we had toys in the bathtub, and one of the things we had was like a cup. And I remember taking a thing and turning it over, and you could hold air in it. Well, the same thing happens here. You have a little bit of water, and you're bubbling whatever it is you're trying to collect inside the cup. But guess what you are also collecting? You're collecting water vapor, because water has a certain vapor pressure, and that's going to be in the next chapter. And you're going to collect water vapor along with whatever it is that you're trying to collect. So you actually have to subtract off. You actually have to know what the vapor pressure is at that particular temperature. And so we have the pressure of NO2 plus the pressure of the water vapor. And you look this up in a table is what you do. You look it up in a table. You look at whatever the pressure is for today. It could be 765 millimeters mercury, or it could be 1.01 atmospheres. And you look up whatever today's pressure is, and then you go to your table and you subtract off whatever that water pressure is. It could be something like 22 millimeters mercury. It's not much. But it is there. And so you don't collect as much as you think you're collecting. That's the bottom line about that. So if you're collecting at, say, 771 millimeters mercury, and the vapor pressure of your water is 22 millimeters mercury, then you're really only collecting, what is that? 40, what is that, 749? Let me see. Let's see. Yep, 749 millimeters mercury is what you actually are collecting. And then you have to plug that into PV equals nRT to figure out, how many moles you actually have, and then you can figure out how many grams you actually have. Okay. Now, if you're working in a factory, if you're working in a chemical factory, this makes a big difference. So this is why it's so important that you know this, is so that when you go up in front of the boss and you say, well, I don't know what happened, we're off by a factor of 5%, and the boss looks at you and says, you do realize you're collecting it over water, right? You don't want to be that person. All right. So there is water vapor in everything that you do if you're going to collect it over water. But it's real easy. You just subtract off whatever it is for that particular day. It's going to be different on different days. All right. So that is partial pressures. Now let's switch gears completely. And let's take a look at something else here. We have something called the speed of gas particles. All right, so The speed, though, is something called the velocity RMS, and that's actually a V, as in the actual velocity. And that is a square root of, I believe it is 3RT over the molecular mass. All right. Now, this is a average velocity. If you look at a sample of particles, and if you were to look and measure the speed, it would follow a distribution that would look something like this. And the number. All right. And RMS is not really the average, but it's pretty close to the average. It's right about there. Okay. And the RMS speed is the root mean squared speed. And basically what it means is that 50% of the particles have a higher kinetic energy and 50% have a lower. So it really represents the average kinetic energy is what it represents. And so what's really cool about this is it's a very easy calculation to do. Like, what is the average speed of the air in your room? And I would say that right now it's roughly around 500 meters per second or so, 540 thereabouts. Okay, but let's see what it really is. Now, when we use this equation here, there are a couple of things that we have to be very careful about. It's 3RT over M. First off, the R that you're going to use is 8.314 joules per mole Kelvin. Okay, it's a different R. The gas law constant that we used before was what, 0.0821, right? And if you were using millimeters mercury or torr, it was 62.4. Here's another R. Like I said, there's about a dozen R's in this world that are in common use. And these are just 3 of them so far. All right. You have to use that R. All right. Now, temperature. What do we know about temperature? If you haven't got it by now, must be in Kelvin. You have to, and when you're doing gas law calculations, everything has to be in Kelvin. All right. Now, here's the part that everybody messes up. M. M is the molar mass, but it must be in kilograms. And you may say to yourself, why in the world does it have to be in kilograms? Everything here is SI units. What's the SI unit for temperature? Kelvin. What's the SI unit for mass? The kilogram. So everything has to be in SI units for this to work. Okay. Now, so having said that, if N2, which is most of what you're breathing right now, is nitrogen gas, 70% of it's nitrogen gas, is 28.0 grams per mole, what's that in kilograms? Well, that's 0.028 kilograms per mole. So you have to be very careful about this. You know, there's 1,000 grams to a kilogram. So the easiest thing to do is just move that decimal point over 3 times. That'll work. Or you can set it up and say, you know, there's 1,000 grams to a kilogram. But here's the thing. It's got to be in kilograms for this equation to work right. And it has everything to do with, it has to be in SI units, but also, you know, the whole definition of joules is in terms of kilograms and acceleration and so forth. So let's put this in here then. And so what do we have? We have 3 times 8.314 joules per mole kilogram. And times temperature, let's say room temperature, 25.0 degrees Celsius. Okay. And so that would be what? This would be 298.2 Kelvin. And then we're going to divide it by the molecular mass of nitrogen. We're going to divide it by molecular mass of nitrogen in kilograms. Okay, it has to be in kilograms. And so we go 0.0280 kilograms per mole. And what do we get here? Well, hopefully we're going to get somewhere around 540 meters per second. I don't remember it off precisely, but I think that's about right. 3.8314 times 298.2 divided by 0.028. Oh, that's not right. Let's see. 3 times 8.314 times 298 divided by 0.028. And then we need to make sure that we go ahead and take the square root of that after we're done. And let's see, still trying to get it in my calculator. Let's see, 3 times 8.314 times 298.2. And we'll take the square root of that. Let's see, where's my square root key? There it is. 515. What did I say? 540, right? Yeah, I was close. 515, 540, 515 meters per second, which means the gas molecules in the very air that you're breathing are covering almost, or about, I don't know, 5 football fields a second. And if you know how big a football field is, it's a ways. And 515 meters per second, that's pretty fast. Now, the reason why you don't feel a breeze that's going that fast is because the gas particles are moving randomly. And they don't move far. They move just a tiny little bit before they run into something, another gas molecule. So they're constantly binging and banging off each other. Now, what can we learn from this equation? Here's the thing. See, I already got it circled in red, and now I'm drawing blue. You see that? The only thing that's important about this equation is how is the velocity affected by the mass of the particle. As a matter of fact, we have a lab which was due Saturday or Sunday, and I moved it till today. And one of the questions is asked is, well, how fast will particles move, or how fast will things diffuse? And it comes down to the mass. Heavy things move slower. It's like in life, heavy things are always slower. Lighter things are always faster, right? And it's the same thing here. With gas particles, the lighter you are, the faster you go. And if you look, where's the mass? The mass is in the, what do we call it in the bottom? The denominator, right? I think that it says the numerator on top, the denominator's on the bottom, whatever. It's on the bottom. It's on the bottom. What does that mean? As mass goes up, what does it do to the velocity? Well, since it's on the bottom half, as you increase the mass, you're going to decrease the velocity. As you decrease the mass, you're going to increase the velocity. All right, and the bottom line is this is how you can tell. So if you have a list, N2, O2, CH4, argon, and you're asked which one goes fastest, which one goes slowest, how would you tell? Well, you'd go through and you'd have to really literally add up whatever the molecular or the molar masses are. You just go through and add them up. Whatever's the lightest is going to go the fastest, and whatever's the heaviest is going to go the slowest. And that's really all that we really care about as far as this goes. Okay. The actual fact that, nitrogen goes 515 meters per second at room temperature, it's nice to know. Okay. Well, we calculated it. There you go. That's how fast it goes. Now, if you were working in, say, a nuclear plant, and you were trying to separate out, say, different isotopes of uranium because you want to build, a power plant or something like that, well, then it becomes important because we have something called diffusion or effusion. We have something called effusion, and it goes like this. It is, and I have to look at the equation because I never use this, and you will never use this either, but it is the square root of the ratio of the masses. And the only way I even remember this as I look here, they crisscross. That's how I remember it. So if you write down by accident R2 over R1, and you say, well, I can remember that they crisscross, that's still good, because those two actually mean the same thing. Okay, so it doesn't matter. What does matter is that they go by, they differ by the square root of the masses. That's what's important. They differ by the square root of the masses. And so they, something heavy is going to move slower, and it's going to fuse out slower, and something lighter is going to fuse out faster. And so what do we mean by that anyway? So we have, say, a small opening. We have a vacuum on this side, and we have all these particles that are moving around. Occasionally they're going to come through the hole. And how fast are they going to go through? Well, they're going to go through, I don't, if you may notice, I don't know if you noticed, but they are very similar. These two equations are very similar. The velocity RMS is how fast these guys are moving. The ratio of how fast they're moving is how whether they're going to come through that opening or not, relative to the other molecules. So if you're big and heavy, you're going to come through a little bit slower. And if you're light and small, you're going to come through a little faster. And it's going to be related to by the square root of the ratio of your masses. And it all comes back to 3RT over M. So once again, what are we really after here? Are we really after and trying to figure out which one's going to diffuse in 1 minute versus 2 minutes? No, what we're after is you have a list of molecules. Which one's going to effuse first? Well, I can tell you which one's going to effuse first. You got to add up the the molecular masses, and then say, well, which one's the lightest? That'll tell you which one's first. Now, from a practical standpoint, there was a method of separating out U-256. Is it U-250? Different isotopes of uranium, U-235. Different isotopes of uranium, one of them goes bang and the other one doesn't. And so to separate them, you would combine them with fluorine, and the good stuff would be a little bit lighter than the heavier stuff. And so it would be very important. And you would make these basically these sieves, the molecular sieves, and you would push the uranium through it, and the lighter stuff would come through first. And if you do that a few thousand times, you can actually enrich what you got. So yeah, it was important for that. But as far as we're concerned, what do we really care about? This is what we really care about. We care what comes out first, what comes out last. How fast? Yeah, not so important. All that really matters is it light? Light means fast, and heavy means slow. Okay, that's what's really important. Light is fast, heavy is slow. You do not have to go through all this trouble of calculating out. Although you can. You can. You just put it in your calculator. That's what you do. All right. All right. So that's a fusion, and that's what that's based on right there. Let's see, what else do we have here? All right, there's something called the van der Waals equation. You may have seen it. If you have looked, and I have to pull up my textbook, I have to actually look in the textbook, and I look at that, and I see this horribly long equation, P plus n squared D over V squared, and it's times some equate. Let's see, V minus NB, and it equals nRT. All right, these terms, you may notice this is very similar to the ideal gas law equation. These terms are correction terms. All right, in other words, you have a table. You know what the gas is, and you have a table in front of you. Those are the numbers that you plug in. You have some, you know, the N is number of moles, and your values that you're going to plug in are going to depend on whatever the gas is. Okay. Ask me, how many people have I ever seen actually use this equation? And the answer is 0. No one ever uses this equation because it is a correction equation. The fact of the matter is that this is for non-ideal. When does that happen? That is for pressures greater than about 10 atmospheres and temperatures less than about 100 K. Okay, those are non-ideal. Now, remember what I said the other day? I said, you know what? Ideal gases do not have interactions, and they're point masses. Real gases have interactions, and they actually have masses and attractions. And so real versus ideal, real gases have volumes. Real gases have interactions. Okay? And of course, there's no and no for that. But what does that really mean? Real gases, since they have volume, the pressure is higher than what you'd expect. And since real gases have interactions, then the pressure is also lower than what you'd expect because they're sucking each other in if they have interactions. Okay. But for the ideal gas law, this works out really well as long as you're under 10 atmospheres or so, and as long as you're relatively warm, and we are, then this works out really well. So will you ever have to do this? Probably not. Probably not. I would only look at the van der Waals equation and I would say, yes, it's an example of how you can take any equation, PV equals nRT, and then you can apply corrections to make it fit better. The pressure term has changed. The volume term has changed, okay? We're applying corrections to it. There's a table for that. So if you're ever in the situation God forbid, like you go out and you work at, say, Aberdeen Proving Grounds, or you end up at Sandia out in, I think it's just outside of Las Vegas or somewhere around there. If you end up in one of these places, yeah, you might have to use this equation, but probably you'll have a table in front of you anyway. Okay, so don't stress about the van der Waals equation. All right, don't stress about it. All right, what else we got here? That is it for chapter 10. So here's what we're going to do. We're going to take a short break, and then we're going to continue on to the next chapter. Okay. All right. So let me go ahead and put up a little notice here that says how long we're going to be gone. So let's say 8 minutes. Let's see, 8 minutes. That would be 10. There you go. All right. So I'll see everybody back at 10:56, and we're going to continue on with the next chapter, and we'll be right on track where we need to be. Alrighty then, we'll get started in a second here. And so, just out of curiosity, what's next up? Let's see. And let's see, test for material. Yeah, don't forget about the quizzes and the homeworks. All right. So, we're going on to chapter 11. Oh, IMFs. IMFs are so much fun. All right. Of course, my idea of fun's a little different from your idea of fun. Yeah, we got IMFs. So, real quick chapter. It's actually not that bad as things go. So we have IMFs. And so this is chapter 11 stuff. All right, before I continue on, does anybody have any questions about the gas loss stuff? All right, it's just it's straight, you've got to see it like I see it, which is it's just straight up plug and chug. It really is. You have the equation, you plug in your numbers, chug it on the calculator, you're done, right? It's not that bad. All right, it's not like chapter 3 and chapter 4. Chapter 3 and 4 are killer, aren't they? And so was chapter 5. Gas laws. Yeah, just don't be that person who uses degrees Celsius. Just don't be that person, right? All right. So, all right. So, what is chapter 11 all about? It's about IMFs, which will not take that long to go through, and it's intermolecular forces. All right, and basically it's the forces in between molecules. All right, and it affects all sorts of things. What does it affect? It affects its freezing points, which is the same as melting, by the way. Melting, freezing, same thing, just two different directions. It affects your freezing points. It affects your vapor pressure. Boiling points. Viscosity. You know, how easy it is to stir something. That's what viscosity is all about, okay? And so it affects all these different things. And so what does it really come down to as far as IMFs go to? First off, you have to know whether something's polar or nonpolar. Polar or nonpolar. Okay. So if something is polar, it's going to have a permanent dipole. Okay. And so if you have something like ammonia, all right, does this thing have a dipole or not? Okay. Polar. All right. Does it have a dipole or not? And if you remember, what do we look for? We look to see is if there's a difference in electronegativity between the different atoms. Okay. But, as far as small molecules go, you look around and you ask yourself, is this the same or different? It's different. So for some reason, I don't remember how to spell polar. Polar. Hold on. So is it polar or non-polar? It's polar. All right, it's polar. And so let me look here. Hold on. All right. So we end up with a partial negative and a partial plus. Okay? So what do we know about charges? We do know that if that their opposites attract and same charges repel. We do know that. And so if I was to have another ammonia, it would actually be attracted to that positive end. Now these guys, if they're in solution, are going to be tumbling around. All right, someone is texting me or doing something. Yeah. And these guys are going to actually be attracted to each other. So they're going to tend to line up like this. Okay, so these guys are lining up. And if you do the same thing with water, they will tend to want to line up head to tail like that. So there is an attraction. There's a plus minus attraction that's going on between these. All right, now, because they're polar, they're going to be attracted to each other more so than if they were not polar. So if we had, say, nitrogen molecules, I'm just trying to illustrate what it means to be IMFs. If we have nitrogen molecules, how are they attracted to each other? They're not really attracted to each other at much at all. They're not attracted to each other much at all. And so the water molecules and the ammonia molecules are very strongly attracted to each other. Now, let's take a look at something like, say, vapor pressure. All right, and how is this affected by the IMFs? Well, vapor pressure, you have a liquid, and from that liquid surface is coming off molecules. All right, so we have, say, above water, and then we have molecules coming off. All right, now, what does it take to get this to go from liquid to a gas? You actually have to break these bonds over here. See these bonds? You actually have to break those bonds. And if you break those bonds, then the water molecules can go into the gas phase. All right. And so when they're part of a liquid, you have these bonds. And so it takes a certain amount of energy, delta E, delta H. All right. And as it goes above. And so if you have a polar molecule, you have to overcome those attractions. If you have a nonpolar molecule, then you don't have to overcome those attractions. And so which one's going to take more energy to vaporize? Well, it's going to take more energy to vaporize something like water as opposed to nitrogen molecules, right? And so what ends up happening here is you actually have a lower vapor pressure for something that's polar versus something that's non-polar. Okay, so you have a lower vapor pressure. All right, so these intermolecular forces, they affect things like vapor pressure, melting point, boiling point, and we're going to do a lab on that as well. So, all right, so what kind of IMFs do we have? All right, the first one called LDF. London dispersion. London dispersion forces, LDF. And here's the big thing about LDF. Everything has it. It's real easy to forget because there are other forces which are relatively stronger than LDF, but everything has LDF. Everything has London dispersion forces. Everything. Now, LDF is weak. LDF is weak. Now, where does LDF come from? Well, it's like this. You take an atom, got a bunch of electrons zipping around. All right, each one of these dots is an electron, and they're moving around, doing their thing. And at any one moment, there's just as many on one side as on the other. And so there's nothing really exciting going on. But every now and then, the electrons will be a little bit more on one side than the other. If they're a little bit more on one side than the other, then this side ends up becoming a partial negative, and this side ends up becoming a partial plus. Just for an instant. Just for an instant. And if it just so happens to be next to an atom that also is experiencing that very rare random occurrence, this side is minus, this side is plus. And guess what we have right here? We have a little bit of an attraction. So for just that instant, they're attracted to each other. This is LDF. All right. And it has to do with the polarizability of the different atoms. Okay. Now, what do you have to have for LDF to happen? You have to have electrons. And you have to have more electrons on one side than the other. What's on the outside of all atoms? Electrons. Okay. So more electrons equals greater LDF. All right, now LDF, London dispersion forces, is weak. Okay, it's weak compared to the other forces that you have. But let me show you something here. Let me show you something here. So let's take a molecule which has nothing but LDF. All right, it's the weakest force. Here's a molecule. In case you're interested, this is called butane. 4 carbons, butane. No double bonds. Okay, this thing has nothing but London dispersion forces going on. And if you park it next to another butane, you may say to yourself, there's not much interactions going on, and there's not. But this is kind of like the way I like to describe this is it's like Velcro. All right, y'all know what Velcro is. Velcro are these little hooks and little loops. That's what Velcro is all about. You got the fuzzy side, that's the loop part, and you got the plastic side. If you've ever seen Velcro, you know it's got a plastic side and it's got a Velcro side. It's got a fabric side. Okay, and when you put these together, what happens? Well, the loop and the hook get tangled up. All right. Now, individually, how strong are these individual connections? They're not very strong at all. If you look at Velcro, the individual little hooks and the fabric that it's grabbing on, if you try to pull them apart, it's super easy. But what happens if you put a whole bunch of them together? If you put a whole bunch of hooks and a whole bunch of loops together, it's actually quite strong. And if you've ever watched Ellen, I think Ellen has this thing where they call it the human Velcro or whatever, and they jump up and you can support a human being on a wall. Well, look what happens here. Individually, between these molecules, you have very weak interactions. You have LDF. LDF's going on all the time. And I'm drawing these little dashes just to show you know that everything is looking at everything. Everything's looking at everything. And individually, these are small interactions. But what do we have here? Over the entire molecule, we have many, many opportunities for LDF interactions. Many, many opportunities. Got LDF, got it between the carbons, you got them between the hydrogens, you got them all over the place. So individually, LDF is small, but it adds up. Okay, so what you can't do is you can't just look at LDF and say, oh well, LDF is small, it doesn't matter. The molecule's big enough they become substantial. They become substantial forces. Okay, so everybody has LDF. All right, now the next one is something called dipole-dipole. And it's strong. All right, it is strong. And so if you take something like sulfur dihydrogen sulfide, which looks like this, it does have a dipole. And it goes this way. Partial negative on that end, partial positive on that end. Okay, it is a polar molecule. And so it will tend to line up with other molecules, and it will tend to line up head to tail, just like this. There you go, head to tail. And it's strong. It is strong. And so that makes a difference. So if you take something that's about the same molecular weight that is not polar, let's say we take sulfur hexafluoride, not polar, non-polar, they're roughly about, and I mean, yeah, the sulfur hexafluoride's a bit heavier than this sulfur dihydrogen sulfide. But the bottom line is this thing has only LDF forces, and the other one has dipole-dipole. And guess what happens to the melting point and the boiling point and all that? This thing is roughly room temperature as far as its melting point goes. It's roughly room temperature. It's a little bit less, I mean, than room temperature, but it's in the grand scheme of things, it is fairly high melting point. Sulfur hexafluoride, I mean, its boiling point is way down there, because it's the boiling point is how much energy does it take to separate it from the liquid into the gas phase. And so if you were going to classify these two, you would look at it and you would say, well, you know what? Sulfur hexafluoride, nonpolar, low boiling point. Polar, it has a high boiling point. All right. Now, can we calculate this? We could, but we're not going to. All right. So this is where our first steps go. As far as, we have to be able to classify things and say, does it have a high boiling point? Does it have a low boiling point? Relatively speaking, hand waving, all right? Hand waving level, all right? And so we would look at something, say, like ammonia. you look at the structure, you always have to look at the structure. You would see that yes, indeed, it is polar. And you would expect, therefore, to have a high boiling point, high viscosity, high melting point. This is what you would expect. Okay, so this chapter is really super easy as far as this goes. It's not about calculating actual values. It's about, what do you expect? So if you look at something that's polar, you expect it to have a high boiling point. If you look at something, you say it's non-polar, you expect it to have a low boiling point. This is the sort of thing that we're looking for here. All right, so this is a pretty good stopping point for this. We will finish this up tomorrow on Tuesday. It will not take long to get through it. It really won't. Chapter 11 and chapter 12 are actually very straightforward. They're more descriptive. Not so much calculations, more what's higher, what's lower kind of thing. Whereas your gas laws, on the other hand, you got to have a calculator handy. All right. So what chapter are we on? 11 and 12, or just 11 and 11 and 13. 11 and 13, not so bad. You still need to go through. Make sure you're working the red problems. Okay, we got one more test to go, and then we have the final, right? Okay, make sure you're working lots and lots of problems. All right, make sure you're working lots and lots of problems out of the chapter. All right. Practice makes perfect. We only got a week left. Yeah, only got a week left. All right, so I will see whoever decides to come tomorrow. You come tomorrow. If you can't make it tomorrow, that's okay. I will post. I will post the record of it. Okay, I will post it. All right. All right. So there you go. Any questions before we go?
I had a question.
Yeah, sure.
So this is about the lab.
Okay.
The discussion question, number 4, it says like using the molar mass you calculated above,
Mm-hmm.
mass of the unknown vapors would be needed to completely fill a
Mm-hmm.
certain milliliter flask. And it gives you the pressure and the temperature.
Right, right.
And so I just wasn't sure if it mattered if like we used the ethanol or the acetone. I'm assuming that's the
Well,
molar mass it's referring to, right?
first off, it doesn't matter which one you use.
Okay.
Okay, so it doesn't matter. And so the second thing about that question is you're not the first one to ask about this, but it's a funny way of asking something that shouldn't be hard to do. And it's like PV equals nRT, right? And we
Yeah.
want to know how many grams, right?
Uh-huh.
Well, what you do is you rearrange the equation. I am sharing, Anna.
Yes.
You rearrange the equation, you've got the moles, and then you say so many grams per mole, right?
Mm-hmm.
And there it is. Okay, so you're just using the molar mass you found. Which was what, 43 or 53, something like that.
Yeah, it was 43.9.
Yeah. You use that number. That's what you're going to plug into here. But you just rearrange this. So you got your pressure. I think it gives it to you in millimeters mercury. You convert it to atmospheres if you want to. Just make sure you're using the right R. Either 0.0821 liters atmospheres moles Kelvin, or you can use 62.4 liters millimeters mercury moles Kelvin. And of course, make sure you're using Kelvin, right?
Okay.
Temperature, and you just solve for M and solve for N and use your molar mass of whatever you found out, and you should end up with somewhere around 0.0 ish. 0.0 ish. All right, I forget what the number is exactly, but it shouldn't be very much. Or maybe, I don't know, if was it 0.0, maybe it was about 1 gram. I don't know, but anyway, you shouldn't end up with a million.
Okay. And so I'm going to calculate and find the N first and then take that
and then you'd use that to use your molar mass, and then you can find your grams from that. Okay. So actually, it's a lot simpler than the question sounds, isn't it?
Yeah.
Yeah, yeah. You just rearrange your ideal gas law. Make sure all your units, which they're not, make sure all your units are in the right form, and then just plug and chug. Get your N from your moles. You can get your grams, right?
Yes.
There you go. Yeah.
And then I also had one more question on homework 10. There was a question about like we were given an unbalanced equation and they wanted us to determine the liters
Mm-hmm.
of O2 consumed at STP. And I
Yeah,
wasn't
you gotta remember that. I think it's 7-3,
um
something like that. 7 moles, O2 to 3 moles. You gotta everything that what people tend to leave off on that problem is the mole ratio. You have to have the balanced equation to get your mole ratio. Once you get the mole ratio, you need to calculate the number of moles. Now,
okay.
since it's assumed at STP, it's 22.4 liters per mole. So once you get the moles, moles cancel, you end up with the liters.
Okay, and so I would just do the 22.4 and then I would do the mole to mole ratio.
Yeah, yeah, you got to get so you got to start with the grams, and then you're going to use that. You got to go from grams to moles, because anytime you got grams, you're going to end up with moles, right? Because you always have to have the molar mass. So it's going to end up being grams. You will use your molar mass to get your moles. Then you would use your mole ratio, 7-3, I think it is. I could be wrong, but it comes off the balanced equation. Use your mole ratio. Once you get the moles of the O2, then you would use your 22.4 liters per mole. You see what I'm saying?
Yes.
Yes. So you would go from the grams to the moles, grams to moles, use your mole ratio to get to the other moles, and then use your STP number, which is 22.4 liters per mole, to get to your
Okay.
liters.
And I would do the molar mass of the C2H6, right? Or would it be the O2?
Well, it's whatever you start with, right? How many grams of what you start with? That would be your molar mass that you would use.
Okay.
Then you would use your mole ratio to get the moles of oxygen.
Okay.
You follow what I'm saying? You got so many grams of this, you need the molar mass of whatever it is you have grams of. The C2, what is it? C2 what? C2
H6.
C2H6. That's ethane. And so, yeah, I mean, so that's what you would use. I mean, you would use your molar mass of the C2H6, however many grams per mole that is. Well, it would be moles over grams. And from there, you would use your mole ratio from your balanced equation, right? Because remember, what's the purpose of the balanced equation? Get your mole ratio, right?
Right.
Yeah, I mean, I think it's. I'm thinking it's 7. Is it 7? 7.
I think, hold on. I haven't,
Well, you have to balance. The bottom line is, I'm just guessing. I'm not even looking at the problem right now.
it's 7-2. It's, yeah.
Is it 7? Yeah,
Yeah.
I was right about that. That's not a bad guess, but yeah. So you use that mole ratio to get your O2,
Okay.
and then from there you use 22.4 liters per mole, and there you go. You got so many liters.
Okay.
All right. Does that make more sense?
Yes, thank you.
Great. I'm glad to help. Other questions? That's a good question. You know what? Everybody asks that. Everybody asks that. So you know what? You're in good company. All right. Well, if nobody has any questions, if you do think of some questions, just email me, okay? Just email me, or let me know you're getting on WebEx, whatever you need. Okay, I'm here to help. Got a week to go. I'm here to help you. Goal here is everybody makes it, right? That's the goal. All right. So I will see y'all if you want to. I'll see y'all tomorrow then. Okay. All right. Bye.